In this section, we are going to talk about the three different types of structs, with the main one being a named field struct. Structs are important because it will help us group together similar values into a one value-like variable. We are also going to go over lifetimes and what they are and why they exist, as well as the history behind them and how they continue to evolve. The concepts that we learn in this section will be continued to get used throughout the lifetime of this course. So it is important to make sure we understand how structs are used, as we will use them very extensively as we continue our journey, as well as lifetimes, because lifetimes are going to influence how we organize our code. Structs, which are short for structures, let you name and package together related values into a single value so that you can deal with them as a single unit. Rust has three types of structs: a named field, tuple-like, and a unit-like. A named field struct gives a name to each component. A tuple-like struct identifies them by the order in which they appear, and a unit-like struct actually has no components at all, which might sound trivial, but we'll be able to make sense of that a little bit later on. But for now, let's start and look at a named field struct. So we create a struct by using the struct keyword and then the name that we want our struct to be. So notice that it is capitalized at the first character. This is known as camel case or Pascal case, and is the desired format that Rust calls for in this situation. So we're creating a struct called user, and now we're going to give it some attributes. And notice how these are key pair values when we do this. So we're going to have active, and it's going to be a Boolean. We're going to have username as a string, and then we're going to say the sign-in count, and it'll be an unsigned 32 integer. So to create a user, let's say let user1 is equal to user. And this is where that key pair value comes into play. So we're going to say active true. So our key is active and our value is true. User name, and we're going to do string from Tyler. And then for our last one, we're going to say our sign-in count, which is our key, and then our value of 0. So how can we access any of this information? Well, we have what's known as the dot notation. So let's print out my username. So we're going to say user1 and then dot, and then now you can see that these attributes appear. So again, I wanted to print out my username, and this dot notation is how we can access the attributes inside of our struct. So now if we run it, I expect it to say Tyler, which is exactly what happened. Alright, so good. So something else that we can do is we can create a function that's going to build our user for us. So in here, we just want to pass in my username, and we want it to be a string, and then we want a user to be returned. So in here, we're going to return a user, and we're going to just leave username, and then we're going to have active as true, and then we're going to auto assign our sign-in count to 1. So what's happening here? So how come we don't have to assign anything to username? Well, it's smart enough to realize, hey, we have a username parameter and a username attribute. So it's automatically going to map those two together. So we don't have to have any logic down here to basically say, hey, username is username, because that's the same thing it's doing, but Rust is smart enough to do that, make that correlation for us. And then we're just going to go ahead and preset in these values for every user that we do this way. So let's go ahead and build a user. So we're going to say let user2 is equal to build user, and then in here we're going to say we want the name to be string from, and we'll do Tyler2. And then let's just go ahead and print out our username again to make sure that worked the way that we were intending. And that's exactly what we got. So we got Tyler2. So now, what are the tuple-like structs that we talked about? So remember, tuple-like structs identify the values by the order in which they appear. So if we come up here and we go struct and capital coordinates, then we can do I32, I32, and then I32. So now we can come down here and say, get rid of that. There we go. All right. So now we can say let chords equal coordinates 1, 2, 3. So it was able to say, okay, we have an I32, another I32, and another I32. And that's all there is to it for the tuple structs. So remember, tuple-like structs identify the values by the order in which they appear. But now, what about a unit-like struct? So a unit-like struct can be done like this. So now we have a unit-like struct. Well, what's the use of this? Well, we've actually already have used a unit struct prior in this course. When we did the 1 to 5 collect method when we were for like a range, when we were populating a vector, the ... is shorthand for the struct value range. So it's range, and it is set up from like start 1 and then end 5. So we will be able to see how these unit-like structs are a little bit more useful when we start to talk about traits a little later on in this course. But for now, the main structs we're going to be using are the named field ones. So what we need to do now is start looking at how we can implement methods on these structs. Methods are similar to functions. They differ because methods are defined within the context of a struct, enum, or trait object. Methods always have their first parameter as self, which is representing the instance of the struct that is calling the method. So let's create a struct real quick called square, and we're going to have the width and height. And then let's create a square, and we're going to say the width is 5 and the height is 5. Alright, so awesome. So we got our square created. So in order to create these methods, we start off with the impl keyword, which stands for implement, and then the name of the struct that we want to implement these on. So we want to implement some methods on a square. And then, just like what's normal with a function, we say function, so fn, area, and then remember, the first parameter is always self, and then in this case, we want to return an unsigned 32, and since we're doing the area, we're going to do width times height. So if we come down here and print this out, we would expect to see 25. And that's exactly what we got. So we can have as many of these functions as we want. So as another one, let's just call what's my width, if I can spell it right. And we're going to refer to self. We're going to return an unsigned 32, and we're just going to return self.width. And again, just to see how this works, let's print it out. Field, not a method. And that's because it's called what's my width. That would help. And we got 5 back. So that's how you create methods with structs. But now what if we want to have a mutable struct? How can we go about that? Well, in here we would need to make square mutable. So now that we did that, so let's create a function called change width. And we're going to obviously accept ourself. And then I also want to say, hey, new width of type u32. And then we're going to say self.width equals new width. So down here, we would say square dot change width, and my new width, we're going to make it 10, which even though now makes it a rectangle, but for the sake of this, we'll say it is still a square. So now if we print it out again, we would expect it to print out 10 now, which it does not. So let's see what my error is. So it says self is a reference, so the data it refers to cannot be written. So we need it to be an mutable. And now that it works. So we updated our width through a mutable reference to the square struct. So it works the same way as we learned in the last section with mutable references, but in this case we had to make our self mutable in the function call, and then we also had to make our variable mutable. So in the next lecture, we're going to look over what lifetimes are, as well as the history and why lifetimes are even in Rust, and what exactly they do for us. In this lecture, we are going to talk about lifetimes, and it is important to note that every reference has a lifetime. Most of the time, lifetimes are implicit and inferred. Some would say that this is Rust's most distinctive feature. The main idea behind lifetimes is to prevent dangling references. So let's set up a quick dangling reference. So we're going to say let r, and then we're going to open up another code block and say let x equals 5, and then we're going to assign a reference of x to r, and then we're going to come down here and we want to try and print out r. So if we run this, we see that it says the borrowed value does not live long enough because x is dropped here, and then here we try to reference r, we tried to use r, which was a reference to x, but x is no longer there. So we have a dangling reference now. And this is where lifetime annotations start to help us think through this code, and it helps the Rust compiler find these dangling references for us ahead of time. So as we dive into what lifetime annotations are, it is important to know that lifetime annotations do not change how long any of the references live. Lifetime annotations just describe the relationships of the lifetimes of multiple references to each other without actually affecting their lifetime. So to set up a lifetime, all we have to do is just use a tick, so one single quote, and then A. You do not have to use an A, but that is what most people will do. So we can do a reference to an integer at 32. We can have a reference with an explicit lifetime setup of an I32, and then we can have a reference that is a mutable with an explicit lifetime. So let's look at a quick function and just try to make a little bit more sense about this. So we're going to just call it an example function, assign here the lifetime, and then inside we're going to have a parameter of x that's going to be a reference with an explicit lifetime stated, and then we're also going to return an explicit lifetime string slice. So what we can see here is that the lifetime annotations indicate that the reference x must live as long as the generic lifetime. So we can see that all the functions using the same lifetime annotation, the parameters using it, and also the string slice. So the function signature is going to tell Rust that for some lifetime of tick A, the function takes parameter x, which is a string slice, and it must live as at least as long as the lifetime of tick A. So when we're returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime for one of the parameters. So what the lifetime being returned here must match at least one parameter being passed in, which in this case we do satisfy. So what exactly are the lifetimes? Why did they start? And why are they in Rust? Because it is a very unique feature. So the history behind lifetimes has evolved as Rust has evolved. So as we've done in past examples, we have had functions that have had references as parameters and a reference returned at the end of the function, but we did not have to specify a lifetime annotation. So why were we able to do that? Well, the reason to this is actually based on the history of Rust. In earlier versions of Rust, the Rust team noticed that programmers were entering the same lifetime annotations constantly. So they were able to add these patterns into the compiler so the borrow checker could infer these lifetimes in certain situations and would no longer need explicit annotations. Knowing this, the Rust language might continue to see these patterns added into the compiler, which will allow programmers to less often add in these explicit lifetime annotations. So far, the compiler uses 3 rules to infer these lifetimes when there aren't explicit annotations. The first rule is that each parameter that is a reference gets its own lifetime parameter. So if we have one parameter, we have one lifetime parameter, tick A. But if we have 2 parameters, then we have 2 lifetime parameters. So we can have tick A and tick B. So just to make that clear, we can have tick A for one parameter, and then we can have tick B for second parameter. And then it continues on. So if you have 3, you have tick C, and so on. But the second rule is if there is exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters, aka the lifetime is assigned to the return value. Lastly, the third rule is if there are multiple input lifetime parameters, but one of them is a reference to the self or a mutable self, and because in that case it is a method, the lifetime of self is assigned to all output life parameters. So lifetime annotations aren't typically needed in methods because it's always going to return the lifetime of self. So let's take a look at an example of why we need lifetime annotations. So we'll do another little one. We'll just kind of modify the one above, and we'll say tick B, and then we'll bring in Y, B, that is a string, and then what did it take here? Expected a lifetime parameter. So we can either return a lifetime of X, or we can return the lifetime of B. But if we do that, notice how X is now squiggly here, and it is saying there's a lifetime mismatch. So that's kind of, so what we're looking at here is the first rule being applied, because we have two lifetime parameters, but you can see that the second rule doesn't apply because there is more than one input lifetime, because we have tick B, and then since there is no self, the third rule does not apply. But we have to have a lifetime annotation on the return value because there was one given to the parameters, and as we learned earlier, when returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime for one of the parameters. So lifetime annotations are required in situations where the borrow checker doesn't know what to infer, and it's important because we want the borrow checker to ensure that we have memory safety. It is possible for structs to hold references, but when we do that, we need to add a lifetime annotation on every reference we created. So let's quickly create a new struct. We're going to call it myString. And then inside of here, we're going to add a text field, and we'll give it a reference to a string slice. So we can tell that we already are getting an error, and it says we're missing a lifetime parameter. So let's give it one. And then also up here, we're going to have to declare it. So now everything is happy. But why do we have to do this? Well, we have to do this because when we create an instance of myString, which let's just go ahead and do that. So we'll create a string from, and then this is my string. And then we're going to create an X, which is going to be a myString instance, and we're going to set it text str1 dot as string slice. So we have to explicitly declare the lifetime because we want to make sure that the instance of myString cannot outlive the reference it holds in its text field, which in this case is string1. Because if myString lives longer than the string we created here, which is what we passed in as a string slice, then we would end up having a dangling reference up here. So that's just a really good example of why lifetime annotations are important and how they're going to help us prevent our code from having dangling references. And then to wrap up this section, I want to talk about static lifetimes. When we give a reference a static lifetime, the reference can live for the entire duration of the program. All string literals have a static lifetime. So let's see what this looks like real quick. So we're going to say let S of a reference with a static lifetime string slice equal I have a static lifetime, and it's valid. So when we give the string literal a static lifetime, the text of the string is stored directly in the program's binary, so it is always available. Some will suggest to use static lifetimes in error messages, but you will want to consider whether you want something to live that long or not. Most lifetime errors will result from dangling references, so it is better to just fix the problem the correct way than to assign it a static lifetime. I hope you enjoyed this assignment and were able to quickly produce the correct solution. We are now going to go over the solution to the assignment. The question for the assignment was create a struct called car with the fields MPG, color, and top speed. Once the struct is created, implement the following methods: set MPG, set color, and set top speed. Once you have created these methods, create a car, provide it with default values, and then set the MPG, color, and top speed, and then print them out. So let's start off with creating our car struct. And in here we need MPG, which will be an I8, our color, which will be a string, and then our top speed, which will be of I16. Now we want to implement a few methods. Our first method is going to be set miles per gallon, and remember we need to reference ourselves. So set miles per gallon is going to take a parameter of an I8, and then in here we are going to say self dot miles per gallon is equal to MPG. So since we are changing a value in here, we now need to make it mutable. So now we have set color, and we are going to also do a mutable self, and our color is going to be a string is equal to color. And then lastly we are going to set our top speed, and our top speed is going to be of I16, and we are going to say self dot top speed is equal to top speed. So now that we have our methods implemented, we can go to main, and now we can create our car. And we're going to need our car to be mutable because we are going to change the values of our MPG, color, and top speed. So we'll say our default values for our MPG is 0, our color is going to be red, and then we will say our top speed is also 0 to start as well. And now to beautify this a little bit, we will say cargo format. I can get rid of that. There we go, cargo format. So now it's a little easier for us to read. So now we can say car dot set miles per gallon. We'll say we get 15 miles to the gallon. We will say our color is blue, and now we will say our top speed is 250. We go really fast in this car. So now we are going to print it out, and we want to print out our car. So there's one thing that we need to add in order for us to be able to print out our car. We need to add the derive debug trait. And now we're able to print out our car, and method top speed, set top speed. And now we see that our car has now been successfully assigned the miles per gallon of 15, the blue color, and a top speed of 250. So I hope you were able to quickly solve this assignment. Again, if you have any questions at any time, please ask them in the Q&A section.